Welcome student to this class of the electrical machine first. Yesterday we were talking about the transformer, and that also at the an ideal transformer we have find out some parameters related to the transformer, that is turn ratio, then the reflected impedance as seen from primary and the secondary. Now today we are going to start with the sorry for the interruption. Today we are going to start with the operation of a non-ideal transformer, that also at no load. Now, what is a non-ideal transformer? So my screen is visible, students?
Yes, sir.
Yes, sir.
Okay. So basically this non-ideal, rather than the non-ideal word, we should use the practical transformer. Okay. So far we have discussed about an ideal transformer in the last class, but now in this class we will discussing about the practical transformer, and that also at no load. No load, you understand, it is open circuited, that is the secondary windings are open circuited, no load is connected. And yesterday I have uploaded an practical of an transformer also on the same channel. Okay, I think most of them you have seen also, and you have liked it also, I think so, is it not?
Yes, sir.
Have you seen the experiment that I have uploaded yesterday? So in
Yes,
the
sir.
in the same way, I will be keeping on uploading the experiments related to your electrical machine. Today also I will upload one experiment related to the open circuit and short circuit test. Okay, so now let us discuss about the practical transformer. Now practical transformer will draw some current. Okay, and that current will be called, now since it is no load, therefore there will be current on the primary side only, because secondary side is open. No load means secondary side is open, so there will be some current that will be drawn on the primary side, and that current will be called as a no load current. And this current is due to the two non-ideal conditions. Okay, the same conditions which we have assumed to be zero in the ideal case, now the same two condition will here, that is the power loss and the core magnetization. Okay, so first is the active power loss. Okay, what are the power loss when the transformer is at no load? There are two types of losses are there. Okay, there are two type of losses are there. One is called hysteresis loss and another is called eddy current loss. Basically they are also called as no load losses or constant losses. So you need not have to confuse between the these two words, because some books use them as a iron loss. Some books considered as named it as an fixed losses, because they are remain as constant. They remain constant whether transform is at no load or it has a half load or quarter load or 3/4 load or full load. At any load there these losses will remain constant, and these losses are known as iron loss and fixed loss. And some of the book have also named as active losses, where rather than this word should not be used, though it is there in my slides, but the proper word is iron loss or fixed loss or constant losses. And there are two types, the hysteresis loss and the eddy current loss. Now you will ask, what is this hysteresis loss? Definitely, is it clear? So what is the hysteresis loss? So let us understand the hysteresis loss. So for that purpose I will draw, now since you know that the core is made up of which material?
Silicon steel.
Yes, silicon, high content silicon steel. Okay, now basically it is an iron only in which the high silicon is being put on. Steel is also type of iron only. Now the iron has a curve called BH curve. What is called that? BH curve. So H is the magnetizing force which is proportional to current, which is proportional to the current, and B is the magnetic field. B is the magnetic field produced due to this current. So let us say my core is initially completely non-magnetized condition. मेरा जो core है वो initially उसके अंदर कोई मैग्नेटिक फील्ड नहीं है. अब मैं करंट बढ़ाता हूं, जीरो से स्टार्ट करता हूं, तो उसमें मैग्नेटिक फील्ड कैसे प्रोड्यूस होगा? मैं कर्व बना रहा हूं, ये देखिए धीरे 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 बढ़ेगा, फिर लीनियर होगा, और उसके बाद अगर आप करंट बढ़ाएंगे तो ये मैग्नेटिक फील्ड कांस्टेंट हो जाएगा. ठीक है, तो पहले इनिशियली मैं एक कुछ पॉइंट तक there is no such cut-in voltage, the cut-in current, there is no such magnetic field is produced. Beyond a particular magnetic current, okay, the current will goes on increasing linearly. So this is the linear portion, this is the linear portion, okay. And then when at a particular limit called knee point, this point is called knee point. घुटने नहीं होते हमारे, knee point. At beyond this, if you increase the current, the magnetic field remain constant. Okay. Now ये कर्व आ गया हमारा. अब एक व्यक्ति कहता है कि मैंने जितना करंट दिया था उसको मैं वापस लेता हूं, आई रिड्यूस इट. ओके, सो व्हाट विल हैपन इफ आई विल रिड्यूस इट, देन व्हाट यू एक्सपेक्ट? आप क्या एक्सपेक्ट करते हैं? फर्स्ट ऑफ ऑल लेट आंसर शुड कम आउट फ्रॉम योर साइड. आपकी तरफ से आंसर आए कि मैंने एक बार करंट बढ़ाया, तब इसने ऐसा कर्व दिया, पहले बढ़ा नहीं, फिर बढ़ा, लीनियर ही बढ़ा, और फिर कांस्टेंट हो गया. ये कहलाता है सैचुरेशन. This is called saturation stage of the transformer. Saturation मतलब now it is no more going to produce any magnetic field. You keep on increasing the current. अगर मैं अब इसमें रिवर्स चलता हूं तो आप क्या एक्सपेक्ट करेंगे आइडियली कि सर अगर मैं करंट को रिड्यूस करूं तो वापस इसी पाथ पे चले, और वापस जब मैं करंट को जीरो कर दूं तो मैग्नेटिक फील्ड कितना हो जाना चाहिए? कितना हो जाना चाहिए? जीरो. डू यू एक्सपेक्ट और नॉट? भाई मैं फॉर्मूले में चला तो करंट आपका इंक्रीज, पहले इंक्रीज नहीं हुआ, फिर लीनियरली इंक्रीज हुआ, फिर सैचुरेशन आ गई. अब मैं रिवर्स में चलता हूं, मैं करंट को रिड्यूस करता हूं, तो आप यही पाथ की उम्मीद करेंगे कि दैट द करंट विल ट्रैवर्स फ्रॉम दिस 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 एंड दिस लाइन. बट एक्चुअली इट डज नॉट हैपन. व्हाट हैपेंस इफ यू विल कीप ऑन इंक्रीजिंग द करंट, देन इट विल टेक दिस, it will take this, it will take this path. So when current is zero, what you are finding? There is some magnetic field is there. Previously at the initial condition, when current was zero, magnetic field was zero. But now some current is there. Now the current is zero, but still it has some magnetic field. This, it means some of the energy which I am providing through source is being lost, and the core has stored in the form of magnetic field. कोर ने क्या किया? कुछ एनर्जी हमसे ले ली. हमने तो ये उम्मीद की थी कि भाई हम एनर्जी दे रहे हैं और वो वापस चाह रहे हैं, तो उसने हमें उतनी एनर्जी नहीं दी जितनी उसको देनी चाहिए थी. तो इस, और उसने वो किस फॉर्म में स्टोर कर दी? मैग्नेटिक फील्ड ने, कोर ने. और इसको हम कहेंगे the hysteresis. This phenomena is called hysteresis, and the energy which is being acquired by the core is called hysteresis loss. The power which is being acquired by the core is called the hysteresis losses. इस कर्व को आप आगे भी बढ़ा सकते हैं. ये जीरो कब होगा? जब आपका करंट रिवर्स डायरेक्शन नेगेटिव में जाएगा, यहां पर जाएगा, और इस प्रकार ये पूरा एक हिस्टेरिसिस कर्व बनता है. मैं आपको पूरा बना के दिखा देता हूं. ये इस प्रकार का ऐसा एक कर्व बनता है, इसको कहते हैं हिस्टेरिसिस कर्व. ओके, और इसके अंदर का जो एरिया होता है दैट रिप्रेजेंट द हिस्टेरिसिस लॉसेस. सो बेसिकली हिस्टेरिसिस लॉसेस इज नथिंग बट द lagging of the magnetic field with respect to the current is called the hysteresis, and the loss corresponding is called, the power loss corresponding to this hysteresis phenomena is called hysteresis loss. So definition: power losses due to repeated changing in the magnetic polarity. अब क्या ये hysteresis phenomena होता है क्या? बिल्कुल होता है. क्यों होता है? Because the current flowing is of which type? करंट जो फ्लो हो रहा है वो किस टाइप का है? AC करंट. ट्रांसफॉर्मर इज बेस्ड ऑन which type of current? Transformer require which type of source? AC or DC? AC source. Is it
AC
clear?
source.
So in AC you have a positive cycle also, you have a negative, you have upward movement, you have a downward movement. So this type of curve is expected in a in a core when AC flows through it. So what happens that a hysteresis curve is formed, and this there is a losses is there due to the repeated change in the magnetic polarity, and this repeated change is due to the flow of the AC current. So in short, you can say that it takes more MFF to demagnetize the core in one direction than the other. देखिए यहाँ हम डीमैग्नेटाइज कर रहे हैं, यहाँ पर क्या कर रहे थे, इस पाथ पे जब चल रहे थे, इस पाथ पे देखिए चल रहे थे, ये फर्स्ट पाथ है मान लो, इस पाथ पे तो मैग्नेटाइज कर रहे थे, फिर हमने रिवर्स किया, इसको डीमैग्नेटाइज करते हैं. जब हमने डीमैग्नेटाइज करने की कोशिश की, तो जब हमने करंट जीरो किया तो हमने पाया अरे इसमें तो कुछ मैग्नेटिज्म रह गया, सब मैग्नेटिक फील्ड इज स्टोर्ड इन इट. ठीक है, इसका मतलब कोर ने हमसे कुछ एनर्जी लेकर स्टोर कर दी, और कोर ने ली है, हमें वापस नहीं दी है, तो हम इसको क्या कहेंगे, लॉस. और इस फिनोमेना को कहते हैं हिस्टेरिसिस. द लैगिंग बिहाइंड इज कॉल्ड द हिस्टेरिसिस, and the loss correspond, the power loss correspond to is called hysteresis loss. And the hysteresis loss remain constant, it remain constant, no doubt. I will give you the formula later on. It is proportional to frequency. Later on we will give you the, but frequency here in our case remain constant. If frequency keep on changing, these hysteresis losses will also change. But since in our case we assume that frequency to be constant 50 Hertz, then the hysteresis loss will also remain constant. Is it clear or not? So the hysteresis loss is clear. Another type of iron loss or constant loss is eddy current loss. Okay, this again happens in the core. So these two losses are due to the core, and since previously the core was made up of iron, nowadays it is iron only, but is a high content silicon steel is there. So in some old textbook you will also refer these two losses combinedly as iron loss. कुछ पुरानी किताबों में अभी भी इनको आयरन लॉस के नाम से जाना जाता है, दोनों को कंबाइंड को हिस्टेरिस लॉस और एडी करंट लॉस. तो हिस्टेरिस लॉस क्लियर हो गया, that due to the repeated change in the magnetic polarity there are some power losses is there, and that power loss is be called as a hysteresis loss. Now what is eddy current loss? What happens now, since AC current is flowing, now what happens that the magnetic flux produced by the windings, the magnetic flux which is produced by the winding, as you have seen the schematic diagram, suppose this is the winding, okay, and it is being put on the core. Now this winding is on what, a core. Okay, so what happens when current flows through winding, flux is produced. So this flux is not only linking the primary and secondary winding, for example here this is secondary winding. Okay, so the flux so produced is not only linking the primary and secondary winding, but it is also linking the core. ये क्या कर रही है, न केवल वाइंडिंग को लिंक कर रहा है, जो मैग्नेटिक फ्लक्स प्रोड्यूस हुआ वो कोर को भी लिंक कर रहा है, और कोर में क्या कर रहा है, ड्यू टू बिकॉज दिस इज दिस मैग्नेटिक फ्लक्स इज आल्सो AC टाइप, बिकॉज AC current is flowing. Okay, so what happens that the AC currents are induced in the iron core in the form of some ED type. ED एक भंवर धाराएं होती है. अगर आपको भंवर धाराएं समझना है तो आप क्या कीजिए, एक स्टैंड स्टिल पानी में एक पत्थर डालिए. इज इट क्लियर? तो आपको क्या है कि ऐसे यूं पानी में धाराएं यूं बहती दिखेगी, इस प्रकार की पानी दूर हटता हुआ धाराएं दिखेगी, उनको हम भंवर धाराएं कहते हैं. तो सिमिलर टाइप ऑफ करंट स्टार्ट्स फ्लोइंग इन द कोर. This induced current starts flowing in the core of the transformer, and this type of current is called eddy current. And because current starts flowing, definitely it has some resistance also, therefore some losses will be there, and that losses in the core due to flow of eddy current is called eddy current losses. So two type of losses are there. One is the hysteresis loss and another is eddy current loss. So how to minimize this hysteresis loss and eddy current loss? As I have already told you in the beginning, that this is not made up of iron. This is made up of high content silicon steel. Okay, so the solution is already being there. They use alloy steel designed for magnetic circuits. Okay, these special type of high content silicon steel alloy core are being used for this transformer rather than the iron core is being used. And how to reduce the eddy current loss? Okay, now that has also I elaborated in the very first class, that we are not using solid core, but we are using a laminated core. So this laminated core will reduce the eddy current loss. No doubt eddy current loss will be there, but it will minimize the effect. Similarly, in high content silicon steel, no doubt hysteresis losses will be there. But what happens by use of high content silicon in the iron? What happens? The hysteresis curve will become very thin. If you use iron, it will be very thick. Okay, to explain this, now let us say that this is BH curve. This is of iron. Okay, so for iron, it is very. I am drawing it. Just see it. Now this is say of iron. Now I am drawing high content silicon steel. So compare these two curves. Okay, the area inside the hysteresis curve represent the hysteresis losses. So which area is more, this one or this one? This is say first one and this is say second one. This is representing iron and this is a high silicon content iron core. So which one will be preferable? Which have more hysteresis loss? First one or second one? अरे सिंपल सा क्वेश्चन है, दो कर्व दिए हैं, ये कर्व देखो बड़ा सा दिख रहा है, तो मैंने क्या बताया, इसके अंदर का जो एरिया होगा वो हिस्टेरेसिस लॉस रिप्रेजेंट करेगा। तो यहाँ पे ये थिन है, ये क्या है, थिक है, तो कर्व किस एरिया किसका ज्यादा हुआ, इसका हुआ, तो इसमें हिस्टेरेसिस लॉस ज्यादा हुआ। ये आयरन को रिप्रेजेंट कर रहा है, ये हाई सिलिकॉन कंटेंट स्टील को रिप्रेजेंट कर रहा है, तो इसमें हिस्टेरेसिस कम हो रहा है, इसलिए हम जो कोर यूज करते हैं वो हाई कंटेंट सिलिकॉन स्टील की यूज करते हैं। उसी प्रकार एडी करंट को रिड्यूस करने के लिए हम सॉलिड आयरन, सॉलिड कोर ना लेकर हम कैसे लेते हैं, लैमिनेटेड। ठीक है, हम क्या करते हैं कि लैमिनेशन मतलब कुछ नहीं है, ऐसे स्टैक्स बना देते हैं, ऐसे बहुत सारे स्टैक्स बना देते हैं, एक सॉलिड कोर को तोड़कर फिर इनको वार्निश लगाकर ज्वाइन कर दिया जाता है। इस प्रकार एक पत्ता लिया, दूसरा पत्ता लिया, तीसरा पत्ता लिया, इन प्रकार इन पत्तों पर वार्निश लगा, इनको ज्वाइन करके वापस कोर बना दी। वो किस प्रकार की कोर कहलाएगी, लैमिनेटेड core, an insulated laminate core. Insulation is done through varnish. Okay, so we have gone through that when a transformer is under the practical operation and that also at the no load condition, then what will happen, two type of losses will occur at no load condition, that is hysteresis loss and the eddy current loss. And to minimize this, we go for the high silicon content steel, and we also go for laminated insulated core in order to reduce it. They are not reduced to zero, but they are being minimized. Any problem so far up to this?
No, sir.
No. अभी तक किसी को कोई दिक्कत कि भाई हिस्टेरेसिस लॉस क्या होता है, एडी करंट लॉस क्या होता है? एक तीसरा हमने आइडियल में माना था कि द परमेबिलिटी इज इनफाइनाइट, बट इन फैक्ट द परमेबिलिटी इज नॉट इनफाइनाइट, इट इज फाइनाइट. सो द रिलक्टेंस, जैसे परमिटिविटी होती है इलेक्ट्रिक फील्ड में, मैग्नेटिक फील्ड में क्या होती है, परमेबिलिटी. इज इट क्लियर? दिस इज नॉट इनफाइनाइट, it is finite. So just resistance is there in the case of electric circuit. In magnetic circuit we have a reluctance. So when permeability is finite, what happens, reluctance will be finite, so some amount of the current will be required to drive the mutual flux between the coil, and that will be proportional to number of turns multiplied by that current. That much of the flux, that much of the current will be required, that much of power will be required in order that the flux should flow mutually between the coils. Okay, so I can express this reluctance as L upon mu upon A. Okay, and also the maximum flux density is given by N into I upon the reluctance, where phi m is the mutual flux between the two coils, and this R is the reluctance. So in terms of inductance, we have L is equal to N square by reluctance. So the core which we assume that in ideal case we assume that it has infinite permeability, it has some inductance associated, and due to which it will cause an inductive reactance, and definitely because of the inductive reactance it will draw some magnetizing current. Okay, because there will be drop across it, therefore it will definitely draw some magnetizing current. So let us talk about that phasor diagram. So everything will be clear that what happens. Suppose this is the applied voltage. Okay, this is my transformer. This is I am showing you the diagram of a transformer. Is my PPT is visible?
Yes, sir.
Okay,
Yes, sir.
so this is my transformer. This is what primary and this is my secondary. Now I am applying a AC voltage source. Okay, and I am keeping this as a open. Secondary is kept open. So what will happen in the no load circuit? This is called no load circuit of a practical transformer. Now I am not talking about ideal transformer. I am talking about non-ideal transformer, that is a practical transformer. So under no load condition, it will draw a current called I naught. Okay, and this current will lag the voltage. Why it will lag the voltage? Can anybody can tell me why it cannot lead? Why it will lag? This is a applied voltage V, angle 0 degree. Okay, with respect to this applied voltage V, this current will lag. This I naught, this is called no load current. इस I naught को क्या कहा जाता है? No load current. It will lag the applied voltage V. Why it will lag? Can anybody can tell me? Because I have already told you that the core is not having infinite permeability, it has a finite permeability, and thus the reluctance to this finite permeability and finite, it has an inductance. Okay, so the resistance is being provided by the windings, okay, and the inductance is being provided by the so-called the core, so-called the core. Therefore now it will have an R as well as XL. It will have a XL. Sorry, this is not I. This is I just want to erase it. It is L. It is L. Okay. So it is not only have a resistance on the winding, but the inductance is also there by the core, and therefore now there will be resistance as well as inductance. Therefore, whenever a resistance inductance is there in a circuit, what will happen? The current will lead or lag? Tell me.
Leg.
Current will definitely will lag. Okay, so current will lag. Okay, this is very clear, and that is being shown in the phasor diagram. Now mind it, phasor diagram is very important in case of in our whole machine. If you understand the machine, you have to understand the phasor diagram. So this is the phasor diagram I have drawn you. This is the applied voltage VT. I have mentioned it by VT angle 0 degree. Okay, now this is the no load current. It is lagging by an angle of say phi naught. It is lagging the applied voltage by angle of phi naught. No, not this is just correct it. This angle is your phi naught. Okay, that is the angle between the applied voltage and the no load current is phi naught, the no load phase angle. Okay, now I will decompose this current into two components. Okay, so one component here I will get I naught cos phi naught, this component, and another component, this component I will resolve into two components. The second component will be I naught sin phi naught. तो एक I naught करंट था, ठीक है, विच इज लैगिंग द वोल्ट अप्लाइड वोल्टेज VT बाय एंगल ऑफ phi naught. मैंने इसको रिजॉल्व किया, दो कंपोनेंट आए हमारे पास। एक कंपोनेंट आया जो एक्स कंपोनेंट था, वो क्या था, आई नॉट कॉस फाई नॉट, जो ये था, जो विच इज इन फेज विद द अप्लाइड वोल्टेज। और एक कंपोनेंट आया जो 90 डिग्री पे था अप्लाइड वोल्टेज के, जिसको मैंने कहा आई नॉट साइन फाई नॉट जीरो। जैसे कॉस फाई नॉट, हम पोलर कोऑर्डिनेट दिए हुए होते हैं तो हम उसको रिजॉल्व करते हैं कि नहीं करते, ठीक है, कार्टेशियन कोऑर्डिनेट में ऐसे ही करते हैं। पी एंगल थीटा दिया हुआ है तो क्या होगा उसका एक्स कंपोनेंट पी कॉस थीटा, और उसका वाई कंपोनेंट क्या होगा पी साइन थीटा। तो यहां पर भी ये दो कंपोनेंट आ गए। ये आई नॉट जो कॉस फाई है ये कहलाता है आई ई। कुछ बुक्स आई ई फी करते हैं या आई ई लिख सकते हैं, इसको कहते हैं कोर लॉस करंट। व्हाट इज दिस? दिस इज नथिंग बट दिस करंट आई नॉट कॉस फाई नॉट जीरो। एक दूसरा जो आया आई नॉट फाइन जीरो, इसको नाम दिया जाता है आई एम। इसको क्या नाम दिया जाता है? आई एम, मैग्नेटाइजिंग करंट। तो नो लोड करंट है वो दो करंट से बना हुआ है। कौन से दो करंट है? एक तो आई नॉट कॉस फाई नॉट जीरो, जिसको हम शॉर्ट में आई ई लिखते हैं। यहां मैंने आई एफ ई लिखा हुआ है, आई ई भी लिख सकते हैं, आई सब्सक्रिप्ट में ई आएगा, जिसको कहते हैं कोर लॉस कंपोनेंट। और कोर, और दूसरा होता है आई नॉट साइन फाई नॉट जीरो, जिसको कहते हैं मैग्नेटाइजिंग करंट, रिप्रेजेंटेड बाय आई एम। ओके, और हम इसको फेजर फॉर्म में कैसे लिख सकते हैं वो मैं आपको लिख के बताऊंगा कि दिस आई नॉट फेजर, नाउ दिस बीइंग ऐसे ही आई नॉट फेजर इज नथिंग बट आई ई फेजर प्लस I am phasor. A very important formula. Is it clear? It is phasor sum. It is not simple addition. What it is? Phasor sum. That is, the no load current is phasor sum of the core loss current and the magnetizing current. And phasor diagram is shown in front of you. This one. इसमें कोई दिक्कत बताइए? ये अगर समझ में आ गया तो आपको आगे की बात भी समझ में आ गई, और अगर ये नहीं समझ में आया then you will very difficult for you to understand the remaining things. Clear? Okay, so the I naught component, component has two component, that is the no load current has two component, the core loss component as well as the magnetizing current component. Okay, so this is the Phasor diagram at no load condition. So you may be asked in the examination, what is the Phasor diagram? Draw the Phasor diagram of a transformer at no load condition. So you will draw this Phasor diagram. Now comes the another thing, how to represent the equivalent circuit diagram of a transformer at no load. So I have shown you, this is the equivalent circuit. Okay, so this is called the so this diagram is the equivalent circuit. Is the PPT visible? All the arrow signs are visible?
Yes, sir.
Okay, fine. So this is the equivalent circuit diagram of an your so-called the transformer, practical transformer at no load. Okay, this is also very important. So what are the components? So previously the schematic diagram I used to draw like this. Like this. This is the representation of core. This is the primary winding. This is the core, and this is my secondary winding. Okay, so that's how I used to represent the transformer. But now I will draw the electrical equivalent circuit of the transformer at no load condition of a practical transformer or a non-ideal transformer. So I have an applied voltage Vt, a current is drawn I naught. Okay, now this current I naught I have resolved into two components. One is IFE or IE. This IFE is called core loss component. Another component is IM. It is called magnetizing current component. Okay, and the total current is also known as, the total I naught is called exciting current or no load current. So you should be familiar with all the terms, because different books, different reference book use different terminology. So you should not get confused. Somebody use I naught as exciting current, somebody use as a no load current. Okay, so you both are the same things. Okay, because no load means because transformer is no load, therefore the current drawn is called no load current. Exciting current, because this current is helpful in exciting the transformer. After that only it will able to perform. Therefore somebody also called this I naught as an exciting current. So now I will draw the equivalent circuit. So I naught has two components. One is IFE, which is, so IFE is what? It is a loss. It is a loss, core loss component. So I will represent, so what will be the value if I divide V by I naught cos phi naught 0. I am dividing a, so I will get V divided by I is what? A impedance, but it is a loss, therefore I will represent it by RFE or simply RE. Okay, here I have written RFE. Okay, I can also write an RE. So what is this? Is the equivalent resistance corresponding to core loss, because whenever loss happens, we always, loss is due to the resistance. Okay, so we represent it by an loss, so we represent it by resistance. So this resistance is, now these two are in parallel because these are two components coordinated to each other. This is 0 degree and this is 90 degree. So I will represent their electrical equivalent in parallel. So in parallel, there is one is there, resistor is there whose value is RFE, and RFE is given by V divided by I naught cos phi naught. Similarly, what I will find, magnetizing current. The magnetizing current is due to the inductance. Magnetizing current is due to the inductance, as I have already told you that now the it is not infinite permeability, it has a finite permeability, and this finite permeability will correspond to finite reluctance, and therefore there will be an inductance. So what will the value of this XM? It will be nothing but applied voltage divided by I naught sin phi naught. XM आपके रिएक्टेंस नहीं होता है, रिएक्टेंस को भी कैसे डिफाइन करते हैं? वोल्टेज डिवाइडेड बाय करंट. वोल्टेज कितना है V और करंट कितना है? मैग्नेटाइजिंग करंट I नॉट साइन नॉट. तो इससे जो वैल्यू आई है वो क्या कहलाएगा? आपके मैग्नेटाइजिंग रिएक्टेंस. मैग्नेटाइजिंग रिएक्टेंस XM. देखिए यहां मैंने इसको, और ये XM कुछ नहीं है, एक इंडक्टेंस है, तो यहां एक इंडक्टर कॉइल को दिखा दिया, यहां एक इंडक्टर कॉइल को दिखा दिया. इज इट क्लियर? और इंडक्टेंस के रूप में दिखाएंगे तो इसकी वैल्यू कितनी होगी? 2 XL की वैल्यू कितनी होती है? 2 पाई F इंटू LM. ओके, तो ये LM, ये बेसिकली IM नहीं, ये LM है बेसिकली. ओके, सो इट इज एन इक्विवेलेंट इंडक्टेंस व्हिच इज रिप्रेजेंटिंग दैट इट इज द ट्रांसफॉर्मर इज ड्राइंग अ मैग्नेटाइजिंग करंट. इज इट क्लियर? ड्यू टू दिस इंडक्टेंस. You got my point? So the equivalent circuit at no load of a practical transformer or a non-ideal transformer, what it consists of? It consists of two parallel branches. Okay, on the primary side it consists of, this is on the primary side because secondary is open. Mind it, secondary is open. This is all, this equivalent circuit on the primary side. It consists of two parallel branches. ये दो parallel branches से बना हुआ है. एक ब्रांच रेजिस्टिव ब्रांच है और एक इंडक्टिव ब्रांच है. रेजिस्टिव ब्रांच को में जो करंट फ्लो होता है वो होता है कोर लॉस कंपोनेंट, और जो इंडक्टिव ब्रांच में जो फ्लो होता है वो होता है मैग्नेटाइजिंग करंट. और इन दोनों को, इनका दोनों का जो फेजर सम है IE और IM का, वो क्या बनता है हमारा? नो लोड प्राइमरी करंट. नो लोड प्राइमरी करंट. सेकेंडरी इज ओपन, देयरफॉर नो करंट इज देयर इन द सेकेंडरी साइड. इज इट क्लियर और नॉट? ये समझ में आया कि नहीं आया? अगर नहीं आया तो आप मुझे या तो माइक को ऑफ करके बोलें या चैट बॉक्स में लिखें. बताइए. Clear? Okay, fine, good. So we have two components, RE and XM, two parallel branches, and that are being shown in the equivalent circuit of a transformer or practical transformer. Two currents, one is the magnetizing current and a core loss current. Okay, and this is the phasor diagram. So in phasors I can again represent this, all these things, that is IFV or IE simply. Most of the books write IE. Here I have written IFV. You need not have to confuse. IE is nothing but VT phasor divided by a resistance RFE, which is equivalent resistance of that core loss component. Similarly, the magnetizing component will be nothing but VT phasor divided by JXM. So it will be inductive in nature, and this will be the phasor sum of this is the phasor sum. Somebody books write phasor represent by putting bar over, or somebody write it below. Okay, you need not have to confuse. Okay, so we can write down that the no load current, no load primary current, is the phasor sum of these two current, core loss component and the magnetizing current. Okay, next come the no load apparent power. Very clear, it is dot product of the applied voltage multiplied by the no load current. So this is the apparent power. Now I can resolve it. What will be the core loss? It will be VT I naught cos phi naught 0. And what will be the reactive power of this? VT I naught sin phi naught 0. So active power is due to the losses in the core, and the reactive power is due to the magnetic field being required in order that the flux should flow from one coil to another. It is very clear. So there are some another formula in order that core loss, what will be the power loss? Okay, you know, you want to calculate this core loss resistance. Now these today we will go for the experiment called no load test and the short circuit test, through which you will come to know about these two parameters, how to calculate these parameters. We can calculate with the help of the no load test. So the formula is PF is equal to VT square upon RF. ये आपको formula मैं पहले भी पढ़ाया होगा कि जो हमारा पावर लॉस होता है वो कई चीजों के बराबर होता है, आई स्क्वायर आर के बराबर भी होता है, या इसको मैं लिख सकता हूं वी स्क्वायर बाय आर भी लिख सकता हूं. तो वो का वो हमने यूटिलाइज किया है कि द पावर लॉस इन द कोर इज नथिंग बट वीटी स्क्वायर अपॉन आर एफ ई. सो I can calculate this, so I can find out this value RFE or RE, that is VT square upon PFE. Similarly, I can calculate XM also. XM I can calculate VT upon IM. How to calculate IM? That IM is nothing but what is I naught sin phi naught. Is it clear? So all these things should be clear in your mind, that by knowing these parameters VT and PFE, you can calculate RFE, or you can also calculate XM by I naught 0. So let us take an example. Okay, so everything will be cleared with the help of this example. So first of all, read the example, what is written in the example. In the example, computing the value of magnetizing reactance and core resistance. That is, we have to compute the magnetizing reactance and core loss resistance, that is XM. What we have to calculate? XM, and we have to calculate RE. Okay, what is given? A 50 kVA. So this is the rating of the transformer. How much it is? 50,000 volt ampere or 50 kVA. What is the voltage rating? 7200 oblique or dash 240. So this is primary voltage and this is your secondary voltage. Can anybody tell me it is a step down or step up transformer? It is a step up or a step down? Yes?
Step down.
Step down. Okay, Ravinder Singh, it is a step down transformer, correct? Because your voltage is being lower down. Your lower voltage is being lower down as you are moving from primary to secondary. What is the frequency? 60 Hz. Which type of transformer? It is a single phase transformer, and it is operating with no load, that is operating at no load. Okay, with the primary connected. Now we have applied the rated voltage to the primary winding. कितना rated voltage कितना है? 7200 volt, और उतना का उतना हमने लगा दिया. ठीक है, तो प्राइमरी में कितना ड्रॉ किया इसने? 248 वॉट. हमने वॉट मीटर लगा दिया, उससे हमें पता पड़ा कि इसने कितनी पावर ड्रॉ की? 248 वॉट. और उस समय इसका नो लोड पावर फैक्टर कितना था? 0.187 लैगिंग. ओके, अब ये कह रहा है ये चारों निकालिए, एक्साइटिंग करंट कंपोनेंट, मैग्नेटोमैग्नेटिक रिएक्टर, एक्सएमएन, कोर लॉस, रिपीट पार्ट इज द ट्रांसफर एनर्जाइज फ्रॉम द सेकेंडरी। देखिए बहुत अच्छे क्वेश्चन है, ठीक है। पहला आप निकालते हैं एक्साइटिंग करंट एंड इट्स कंपोनेंट। कैसे निकालेंगे, आप में से कोई बता सकता है? एनीबडी? वेरी सिंपल, ओके। वी हैव गिवन द नो लोड पावर 248 watt we have given, or also we have given the power factor as 0.187. Clear? So wattmeter measure always active power. This you have to keep in mind. Wattmeter measures always active power, not the reactive power. So what wattmeter is measuring? V I naught cos phi naught. Okay, and that is given how much? 248. V is how much? This is equal to 248. This is given how much? 7200. So you also given the cos phi naught. How much it is? 0.180. So can you calculate the no load current? Yes, you can easily calculate no load current. So you can also do like this also, as they have done it. So no load current comes out to be the same thing we have used, what I have told you, 248 divided by 7200 divided by 0.187. Okay, so it will come out to be 0.1842 ampere. Okay, this is the current, no load current. Clear? Okay, so no load current is clear. Now with the help of this no load current you can calculate the other, that is, this has two components. One is IE, exciting. So exciting current is known to you, that is no load current. Now you can calculate the what else has been asked. Let us see. Exciting current, that is no load current, and its component. Its component is also being asked. So how to find out component? Very simple. Very simple. How to find out? We know that IM, magnetizing current, is nothing but I naught sin phi naught 0, and IE, that is core loss component, is nothing but I naught cos phi 0. We know phi 0, cos phi 0 is how much? 0.187. So can you find out theta, phi naught? That is phi naught, it should be phi naught. How much it comes out to be? 79.2 degree. Now it is lagging, therefore I naught will be 0.1842. It will be minus 79.2 degree. Minus 7, because it is lagging. Minus, so it should be minus. Okay. So once we have found out the current in the phasor form, now we can calculate I naught is magnitude is how much? 0.1842 multiply by sine of 79.2 degree. Is it clear? You calculate it. Similarly, how much this will be? 0.1842. Cos phi naught is already given how much? 0.187 multiply by 0.187. Okay, so you just substitute this value, you will get these two components. Okay, so this is the magnetizing component and this is the core loss component. Is it clear, or any doubt? Then please write in the chat box, I can again explain you. Yes, any doubt? How to calculate exciting current? Calculate exciting current. Okay, I naught, then calculate phi naught, then resolve these two. Your IE will be nothing but I naught cos phi naught 0 and IM will be nothing but I naught sine phi naught 0. And this is the phasor diagram. So for phasor diagram, draw a straight line Vt at an angle of 0 degree. Now draw and current I naught of magnitude, whatever this is there, 0.842 at an angle of theta in a lagging case, that is in clockwise direction, minus 79.2 degree. Then you can also draw an angle at 90 degree of value, how much? 0.809, and you can also cut a value of 0.035 from here, that will represent or IFE. Then this is IFE and this is your IF. Clear? So both concepts are clear, how that under no load condition a practical transformer, how it behaves. It has two components, the core loss component and the magnetizing component, and it is lagging in nature. B part. Find the value of core loss resistance and magnetizing reactance. Very important. Okay, so that you can easily find out how, as I've already told you, what is RF, what is RE. RE will be nothing but V square upon P. So you can calculate it. Vp square upon RE. Vp is already given 7200 volt. Square it. Power, no load power is already given 248 watt. You divide it, it comes out to be 209032. So you can imagine how high this value is. It is a very high resistance. So next, XM, nothing but Vp divided by Im. Im we have already calculated, and Vp is nothing but 7200 volt. So again it comes out to be the inductive reactance turned out to be 39,801 ohm. Okay, and equivalently this is represented, this is the no load current. These are the two parallel branches. One is representing the core loss resistance and another is the magnetizing current inductance. Is it clear? So that's how we have to represent. The third is find the same parameter on secondary side, power constant through transformer. Okay, so the same is being applied on the secondary side. Okay, here again the power drawn, active power is 248 watt. Okay, now applied voltage is 240 volt. Okay, and we can calculate the corresponding the magnetizing volt ampere and this VSIS. So from that we will get the secondary current as 1326 upon 2 divided by 240. We will get the secondary current as the 5.525 ampere. Clear? How we have calculated this value? This value is already known to you. Okay, the angle is clear, very clear. Now with the help of this secondary current, we can calculate the corresponding the no load current component, that is secondary current is 5.525 cos of 79, that is come out to be 1.035. Similarly, magnetizing current is secondary current, no load current multiplied by sine of phi naught, it comes out to be 5.427 ampere. So the same experiment is being performed on the secondary side. We can calculate, compute RFE and XM. Okay, the same procedure, that is V square upon the total power 240 square upon it count 230 ohm. Okay, similarly XM we can calculate it. It comes out to be 44.2 ohm. Compare using turn ratio transformer. Okay, we can compare it also with the turn ratio transformer. It is exactly the same value as we have obtained practically. Is it clear? So what we have learned so far in this case, that we have gone through the non-ideal behavior of the transformer at no load condition, and we have also drawn its phasor diagram, and we have also drawn its equivalent circuit, and we have also carried out one numerical. Okay, so is there any problem so far in understanding any concept? Then you can just tell me now, or you can also write down the chat box of the YouTube. Okay, so that I can, in the comment section of the YouTube, so that I can reply in a better way, or I am ready here also to reply. So any doubt here so far? Yes? I think so. All load is being taken by Eddy Current only, that he will only reply, other will remain silent. Okay. Other all are, I think so, in a sleep mode. Tushar, no doubt. Okay. Because I am ready to clear your doubt. Ravinder Singh. Okay, bye bye. Fine.
No doubt, sir.
Malav, no doubt. Okay, fine, very good. Very good. Means my students have no doubt. Yes, you can do it. The same thing in the lab, in your file. Okay. Yes, Adhikari, it is very clear. You do this thing in the file work also. So whenever you will come to your class, you have to submit it. Okay, so today also I will upload another experiment, that is the open circuit test and short circuit test of a transformer to find out these parameters, these no load parameters, okay, and the equivalent circuit parameters with the help of the two practically experiment. Okay, so thank you very much.